Welcome to the second online lecture of BME306. Today we're going to be introducing the concept of convolution. So we'll start off with providing the integral definition of convolution. So suppose you have two signals that are functions of time, x of t and h of t. The convolution, usually symbolized as x star h, is defined by the following integrals. We'll usually be focusing or using the second form here. So y of t is equal to the integral over all time of the product of h of t minus tau, x of tau d tau. So you'll notice that the variable of integration here is tau, and the resulting function is of time. So let's look back and recall our integral definition of the cross correlation. So we have rxy of tau, the delay, is equal to the integral over all of time of x of t, y conjugate of t minus tau. We'll see there are a lot of similarities and there are a few differences between convolution and cross correlation. So first off, the similarities. They both involve the time shifting properties. So we have h of t minus tau and we have y conjugate of t minus tau. Both require integrating over a time variable. In one case we have d tau, in one case we have dt. There's also several differences. So the differences are convolution requires that one of the signals is time reversed, and we'll get into this in a few examples. But you can see we have the integral of the variable of integration is tau, and we have a function of h of minus tau. So you should recall that if you have an h of minus t or h of minus tau, that's a time reversal property of functions. Second thing to note is that convolution does not use the complex conjugate. So we have this complex conjugate in the definition of cross correlation. We don't have a complex conjugate in convolution. Finally, convolution is very, very important in the analysis of linear systems, but people generally find it a bit more difficult to get an intuitive feel for what convolution is. And that's why I introduced cross correlation first. So cross correlation, as a function of the delay between two signals, just remember that it was a measure of similarity between the signals, and this tau variable shows you where in time the delay of where the signals are most similar. So it's a pretty intuitive to get a feeling for what the cross correlation is. It's not so intuitive for a lot of people to get the same sort of intuition of what convolution does. Although convolution is used a lot and probably more so than cross correlation. So you're probably wondering why we changed the variables for the definition of convolution. So we have an x of t and h of t, whereas previously we had an x of t and a y of t. And you'll notice that I specified the output of convolution as a y of t. And the reason that we do this is because usually we think of x of t as an input to the system, y of t being the output of the system, and an h of t as being the system response. And using convolution, we can reconstruct the output of a system by convolving the input with the system response. So for example, if I just have a linear time invariant system, it's often thought of as a black box. But for example, if you had a circuit diagram with a resistor and a capacitor, you can specify, you can create a mathematical relationship between the output and the input and define that as h of t. And once you have that definition of h of t, you can predict any output for any input using the convolution. So that's why we change the variable names. Usually we have a system input, we have a system response, sometimes it's called a system filter, and then we have the output. So pretty important concepts here. Alright, so let's try to get a feeling for what this h of t minus tau is and what it does. So let's say we have h of t, this is a straight line, so h of t equals t, straight line with no offset. We want to rewrite this as a function of tau, so we just replace all of t's with tau. So we have h of tau is equal to tau. It's still a straight line function. What we're really interested in is h of t minus tau. So let's do a variable substitution. So let x equals t minus tau. Solve for tau. That gives us tau is equal to t minus x. We have this function h of x is equal to t minus x. Let's get a feel for what that looks like. So if t equals 0, for example. So when t equals 0, h of x is equal to minus x. So we still have a straight line function, but it's been flipped about the horizontal axis. So it's no longer a straight line with a positive slope. It's been flipped about the horizontal axis, and it's a straight line with a negative slope. What happens when we have t's are less than 0? So t equals minus 2, for example. So h of x is equal to minus x minus 2. This is again the equation of a straight line that's been shifted down with a minus 2 offset. If you look at this entire function, this entire straight line function has been shifted left. And similarly, if t is positive, we get, for example, t is positive 2, h of x is equal to minus x plus 2. This shifts the function to the right. So what we're seeing is this h of t minus tau has there are two properties. So one is it gets flipped about the vertical axis. So it gets flipped about the vertical axis, and then it gets shifted left or right. So we have the time shifting property, then we have the time reversal property. This is just to give you a feel for what we're going to do in some of the examples that are coming up. Alright, so let's do an example of a convolution problem, and we'll do it graphically like we did with the cross correlation. So let's say we have an x of t, and it's a delta function shifted over 3 time units, and we have an h of t that's in the region specified is a straight line. So it's a straight line with a slope of minus a half and an offset of linear offset of 1, or an intercept of 1. So the first thing we want to do is we want to rewrite the functions in terms of tau. So we'll substitute tau everywhere that we see a t. So we get delta of tau minus 3. And then we want to have h of t minus tau. So recall from a couple of slides ago that h of t minus tau, we have to flip the function about its vertical axis, and then we shift it. So for example, we have h of t minus tau. For tau is equal to minus 5. This function is flipped about its vertical axis and shifted over left. Then similar to the cross correlation, we multiply these two functions together. We get 0 everywhere. We integrate the area under the curve. In this case, it happens to be 0. It's 0 everywhere until the function starts to overlap. Recall that the delta function, it's a height of infinity, but the area is specified to be 1 unless there's a coefficient out front of here. So we have something that has an area of 1 multiplied by this function. It just actually replaces the value of the function. That's what the delta function does. So again, this is the product of the two functions, h of t minus tau and x of tau. So we integrate the area underneath this curve, and we get the value, which in this case would be 1. We continue to shift the h of t minus tau across. The value is, the area is always 1, so we get the value of this function. You could see that the convolution of anything with a delta function simply copies the function that's being convolved. So if you convolve something with a delta function, what you get is you get a copy of the function. This is an important property that's going to be useful to us later on. So this is just a real brief introduction to convolution with a simple example, and we'll go over many more examples in class to get a good feeling for what convolution is, and try to get an intuitive feel for what it does as well.